Hi, my name is Anavi. I'm a software engineer, but I also enjoy creating open source hardware. In the next 20 minutes, I'll share my experience how to add a double EEPROM with device tree overlay to your Raspberry Pi head. It's a great honor for me to be here with you at Pi Wars 2020 at Home Conference. Huge thanks to all volunteers organizing this wonderful event. My talk features three topics. Raspberry Pi heads, just a brief introduction. I'm sure most of you are already familiar with the concept. I'll explain what is a double EEPROM, what is a device tree and device tree overlay. Finally, we'll wrap it up with some conclusions. So a Raspberry Pi head stands for hardware attached on top. It's a specification by the Raspberry Pi Foundation. The form factor and the dimensions should follow some mechanical requirements. The head is bigger. It's for a full-sized Raspberry Pi, such as Raspberry Pi 3 or 4, and the micro head is for smaller form factor compatible with Raspberry Pi 0. In order to call an add-on board a head, it must have a 40-pin header compatible with Raspberry Pi B Plus and all newer models, considering Raspberry Pi B Plus was released on the market 7 years ago. Most of the Raspberry Pis we're using nowadays are already with 40-pin header. Last but not least, the Raspberry Pi head must have an EEPROM with device tree fragment. There are a lot of details and resources how to create Raspberry Pi head. Even a couple of years ago at Pi Wars mini conference in Cambridge, I had a short talk sharing my experience how to design one with the free and open source software KiCad. I have already designed a few add-on boards that follow the specifications of the Raspberry Pi Foundation for microheads. However, I created them even before some of these boards were created before the release of the standard by the Raspberry Pi Foundation, and although they are fully compliant with it, they are called FATs. On the left, there is a board for scanning infrared remote controls and sending infrared signals. In the middle, there is a board for controlling 12-volt RGB LEDs. On the right, is a very simple board that's acting as a joystick for my RetroPie setup. There are some similarities between these boards, no matter that they have completely different use cases. One of the important similarities is the EEPROM. I'm using a through-hole EEPROM on all these boards. I'll now explain you what is a double EEPROM and why it's important for a Raspberry Pi add-on board. So EEPROM or double EEPROM stands for electrically erasable programmable read-only memory. Historically, it dates back from the mid-70s. The EEPROM uses a parallel or a serial interface for data input and output. The serial interface, which is commonly used nowadays, could be a SPI, I2C, one wire, and other serial interfaces. Raspberry Pi uses I2C. The EEPROM is non-volatile, which means that the saved data is not lost on power down. You can turn off the power on the device to which the EEPROM is connected, and the memory will stay there. There is a limited number of reads, and data can be rewritten, changed. Although the name contains read-only memory, actually you can rewrite the data, and I'm going to show you how to do this. In terms of hardware, the EEPROM requires 2 transistors per bit. So what should we have on an EEPROM that we attach to a Raspberry Pi through our head? Well, basically, we need 4 things. First of all, we need vendor information, name of the manufacturer, name of the model of the Raspberry Pi head, of course, version, hardware version. There must be a GPIO map, also a valid device tree information, and it must be connected to the secondary I2C interface on the Raspberry Pi, which is on pins 27 and 28. The Raspberry Pi Foundation, as part of the specifications for the Raspberry Pi head, provided instructions and reference schematics how to connect a double EEPROM to these pins 27 and 28 over the I2C interface. The schematic works at 3.3 volts and it's for 32 kbit EEPROM organized like 4K by 8. You can this is the model given in the reference. However, you can use another model that fits the same requirements. So here is an example of the schematics that I created for my board, the infrared FAT. Here is the board. These are the schematics designed in KiCad. In the purple square, you can see the schematics for the EEPROM. And in KiCad, first you design the schematics, assign footprints. After that, you export these schematics, import them into a PCB layout, and you create a board. So this is the board after all these things have been done. And here you can see the big true hole EEPROM that I'm using. So what is the difference between true hole and surface mount? Well, surface mount technology is suitable for pick and place machines, which means robots that assemble the components on the printed circuit boards. The surface mount components in general have smaller sizes, especially valid for EEPROMs. Nowadays they're cheaper, and the disadvantage of the surface mount technology that these components are difficult to solder at home unless you have a pick and place machine. Nowadays there are some projects for having a smaller pick and place machines, but it's very rare to have someone with a pick and place machine at home. Most commonly people grab a soldering iron and solder things, components to the PCBs at home. So therefore, this is the advantage of the true hole technology for the EEPROM. You can mount it on a breadboard, you can solder it easily. Of course, the disadvantages are the big size. It's slightly more expensive, but in general, EEPROMs are super cheap, so we're speaking about a very modest difference of a few cents. The problem is that true hole components are not often used by the industry nowadays, and it's very hard to find them. Things are moving, everything is moving to smaller and smaller electronics, which means that for industrial things, companies prefer using surface mount technology. If you want to make a Raspberry Pi out on boards, like 1 million units of this board, you're gonna go with a surface mount technology because it's gonna be simpler. If you're making a small manufacturing, if you need to play over the weekend with an EEPROM, you better go with a true hole technology EEPROM because it's gonna be easier for you. So the EEPROM contains device tree binary overlay. In order to understand what is a device tree binary overlay, first we should understand what is a device tree. This is a specification for a software data structure that describes hardware components. It allowed compiled kernels to support different hardware configuration with a wider range of architectures. This means that you can have the same kernel running on Raspberry Pi 3 or 4 or another version and use the device tree with it. The device tree is compiled as an external file from the Linux kernel binary files. The files of the device tree is called device tree blob. It's a binary file with extension DTB. It's compiled from source, and the device tree source is called DTS. A lot of resources, what is a device tree, are available at devicetree.org, as well as very interesting presentation, which is almost a decade old, but still very useful, which is available at elinux.org. Now, let's have a closer look at device tree overlays. Device tree overlay enables a central device tree blob to be overlaid on the device tree. Device tree includes a number of fragments. With the default bootloader on Raspberry Pi, the DTO can be set at config.txt file on the FAT partition, the boot partition of Raspberry Pi OS. As I've explained, the EEPROM on Raspberry Pi on board must be connected to the secondary I2C interface on pins 27 and 28, and it should include this device tree overlay. If you boot Raspberry Pi with attached head with an EEPROM and Raspberry Pi OS, after booting, you will see information about the head at /proc/device3/head. Keep in mind this information is populated at boot time, so if you it's not recommended to do hot swaps. It's recommended to turn off the Raspberry Pi, then put your head, and then boot the Raspberry Pi. However, if you do a hot swap, which is not recommended, then you need to reboot the Raspberry Pi in order to see this device tree information from the user space. In order to compile a device tree or a device tree binary overlay, you need a compiler. It's called device tree compiler, and it's super easy to install it. Just open a terminal, type in sudo apt install device tree compiler, and you have it. Once you have it, the usage is simple. It converts a DTS file. Here is an example, which is actually part of something that I'm using for my Raspberry Pi FATs, and it converts it to either a DTB file like a device tree, or in this case device tree binary overlay. Furthermore, the Raspberry Pi Foundation provides utilities to create, flash, and dump head EEPROM images. There are 3 utilities. All of them are available from GitHub repository. In order to install them on your Raspberry Pi, first clone the Git repository. After that, run make and make install. There are 3 tools. The first tool is called EEP make. It parses the EEPROM text file and creates a binary EEP file. Then the tool EEP flash is used to write this EEP file to the double EEPROM. And there's another tool which is useful for debugging purposes. It's called EEP dump, which dumps a binary EEP file as a human readable text. As I repeat, this is for debugging purposes. The other 2 tools are very useful, first to create EEP file and then to flash it. Here is an example which creates device tree overlay for mapping buttons connected to GPIOs on the Raspberry Pi header to Linux key codes. In order to choose the proper key code, there is this file which is shared between the kernel and the device tree, which includes the definitions of the key codes. And here in this example, we are mapping a button connected to GPIO 17 on the Raspberry Pi to the right arrow key. Once we have the DTS file ready, we are using device tree compiler, which I've explained you how to install in order to create the device tree binary overlay. Then we have to create a settings.txt file, which is actually available as a template from the heads repository provided by the Raspberry Pi Foundation. Based on this settings file with the EEP make command, we're gonna create binary files, the EEP files, which we will after that flash with the EEP flash tool. The example, the fragment, the device tree fragment here is taken from this example, which is available in GitHub. And here is how, after we have all these bits, how to flash them. As I said, Raspberry Pi has 2 I2C buses. The first bus is available at pins 3 and 5, and we can use these pins to flash the EEPROM. Here I have created a do-it-yourself board with a breadboard for flashing through-hole EEPROMs. So on the left is the setup for writing the information on the EEPROM. After that, here on the right, I can move this EEPROM, reboot the board to verify, to test that it's properly flashed. Here, this part of the board is connected to pins 27 and 28, as explained. The flash procedure is done with the ESP flash tool, and after flashing and after moving the EEPROM to the right side to pins 27 and 28 and rebooting the Raspberry Pi, what I'm going to see in /proc/device tree/head, if I boot this board, the Anavi infrared FAT, is going to be the vendor information, the product name Anavi infrared FAT, and the vendor Anavi. So if you want to use SMT EEPROMs instead of through-hole, you can still use similar procedure for flashing. However, you can use sockets like these. These are sockets which are made for attaching SMT components and converting them to through-hole for convenience. Okay, so one more thing. It's about open source hardware soldering kit that I've created. It's called Anavi Smiley. I created it a year ago before the previous edition of Pi Wars, and some of the winners of this competition will get as a small gift from the organizers these soldering kits. These soldering kits are useful for educational purposes. The kit is super simple, just 2 LEDs and a button. Super simple to solder because there are only through-hole components on it. However, apart from learning programming languages and blinking LEDs, you can learn also device tree. And here is a simple device tree source that I have created. And I have already put it here on this Raspberry Pi 4 with Anavi Smiley. So if we have a closer look, there are two LEDs. One of the LEDs is for the heartbeat. The green LED is for the Linux kernel heartbeat. It indicates that the kernel is working. The other one is showing the CPU activity. So if I log in remotely to a Raspberry Pi and make it work a little bit more, you see that the red LED is blinking more because the CPU is doing something. In this case, I just run a sudo update. So let's have a closer look how we can use device tree overlay with this simple board, because obviously this board doesn't have an EEPROM and it's not automatically loaded. Therefore, we need to manually compile it and place it in a specific directory. Anavi Smiley DTS is available in GitHub as an example. We need to use the device tree compiler as we did in the previous slides to compile a device tree binary overlay. Then we need to copy this device tree binary overlay to the overlays directory on the FAT partition on the Raspberry Pi OS. And then we need to manually enable the device tree overlay by editing the boot config.txt file. This is the configuration file that the default bootloader on the Raspberry Pi is looking for. First, we are setting the device tree overlay variable, and we are specifying Anavi Smiley. And then the second line is actually more interesting because it sets GPO26 to pull up mode. This is the GPO in this particular setup where I have placed the add-on board. This is the GPIO for the button, and if you have a closer look on the soldering kit, there are resistors for the LEDs, but there is no resistor for the button. Therefore, we are relying on the internal resistor available on the Raspberry Pi, and in order to use it, we are setting this command. We need to reboot in order to the changes to take effect. Then we need to make sure that the board is attached to these pins. If we attach them to a different pins, we need to reconfigure the config.txt file as well as to recompile the binary blob according to the other pins that we've placed. So yeah, this is a simple example that even with such a simple board, we can use device tree binary overlays. And if you convert it to a Raspberry Pi hat, or if you just use a breadboard to attach an EEPROM, you can skip the manual steps and have the EEPROM automatically detect that this is the board and this is how we use it. Let's wrap up this talk with a few conclusions. Device tree is a software data structure that describes hardware components and provides support of different hardware configuration without recompiling the Linux kernel. The device tree overlay allows extending existing device tree configuration. It's especially convenient for add-on boards, specifically for Raspberry Pi hats. Each Raspberry Pi hat must have an EEPROM attached to pins 27 and 28. If you create an add-on board for Raspberry Pi without an EEPROM like Anavi Smiley, then it's not a hat, it's just an add-on board. Raspberry Pi Foundation provides a lot of resources as well as utilities to flash, dump, and create hat EEPROM images. With an EEPROM, you can automatically configure Raspberry Pi add-on boards, especially hats. This is super user-friendly and convenient because all the user has to do is to plug the board to power on the Raspberry Pi, and the EEPROM will tell the kernel and the user space important information to auto-configure it. Thank you very much for watching this presentation. I hope it was interesting. I hope you've enjoyed it, and I'm happy to hear your questions. Thank you once again.